Yeah. Thank you for reminding me. I keep forgetting. So, all right, let's start. So good morning. Yeah, thanks for coming. Somehow, Srijato, there are three of you, four now. I don't know, somehow your device is misbehaving, I think. So Srijato, can you hear me? No. So let's start. Oh, he doesn't even have his microphone. Okay. Okay. So I hope, anyway, since everything is being recorded, we'll start. So last time we were talking about duality, and I mentioned a way of deriving the strong duality theorem, that is the dual and primal. I mean, when the primal has an optimal solution, then the dual also has an optimal solution, and they actually match. Okay. And this theorem we derived using the simplex method, but we did it for a particular kind of LP where this was in equational form already. Okay. And when we ran that LP, ran simplex on that LP, because there is an optimal solution, we would have reached a certain state. And by analyzing that state, we extracted a solution for the dual. And we observed that the solution that we extracted out of the primal, out of these simplex tableau, the final simplex tableau, actually the value, the objective function that it gives matches the primal objective value. And at that point, I had promised somehow that I will do it for a slightly more general LP. And so let us do that now. It's roughly the same thing, but as a warm-up till other people come, if they come. Let us work with an LP that you are more likely to see in your algorithms course, etc. So, and here you have this LP. So you're trying to maximize this objective function subject to some constraints, and you have non-negativity constraints here. And if you do the usual dual for this LP, the rules will tell you that the dual that you obtain is this. Okay, this is somewhat, there is a pleasant symmetry.
Kumar, it should be greater than or equal to, right?
Yeah. Thank you. So thank you. So we have this LP, and the strong duality says that if the primal has an optimal solution, then the dual has an optimal solution, and the two solutions are equal. So now I would like to, go over the simplex method again and see why this follows from the simplex method. Yeah. So what would we do in the simplex method? We would first, because we have learned simplex method for only the equational form, so we would add some slack variables here, and and we would write this inequality as an equality. Okay. And we would set the slack variables also to be at least 0. And in matrix terms, what we have done is the original matrix A, we have extended it with an identity matrix here. Okay. So, I mean, all this you are familiar with. Okay. And now we are free to run the simplex method on this LP. And when we do that, let us say we come to this tab. Okay. So right now, we are not going to worry about various operations that we performed to get to this tableau, we know that what simplex produces at any stage is a basic feasible solution. That is, it takes a certain invertible, non-singular square submatrix B of this extended matrix, and then it obtains some solution. And we last time checked that the XB and the optimum have this form. Now, from this, we are going to claim that there is some Y. So now we are trying to extract a dual solution out of this situation that simplex brought us to. Okay. And last time we just said that, look, this final optimal was obtained from the original final. So we had the original objective function, and the final row, last row of the simplex tableau was obtained by starting with the original objective function, which used to be written as C transpose X, and adding some multiples of this equation. This equation is this is the right hand side. So we write AX equals B. I have moved everything to the right, so it becomes 0 equals B minus this quantity. Okay, so we have added a bunch of zeros actually to this, but the side effect of that is somehow the basic variables get cancelled in the expression for the objective function, which is in the last row. Okay, and this is how we argued last time. We said everything is just adding multiples of one equation to the other, so there ought to be a Y. Okay, yeah. Now, this time we'll be slightly more explicit. Okay, so yeah. So now, actually, we can guess Y from this already. Yeah. So we were just being a little lazy. We said, oh, we have just added some multiples of those equations to the last line, so there must be some Y. But we can actually be explicit. We can say what that Y should be. And I would like you to help me with this. So what do we have? Suppose, so this is a single line. Huh? This is a matrix with only one line. And this is a matrix with m rows and n plus m columns. Yeah, n plus m columns and m rows. Okay. And suppose there is some we have multiplied these rows by some constant, some scalars y, and managed to cancel all of this. Okay, these were the basic coefficients of the objective function corresponding to the current basis, the final basis. Okay, this is the final basis. Okay. Now we know that this is an invertible matrix. Okay, so there must be a unique y that you can multiply this matrix by on the right to produce this number. There is a negative sign already here, so we don't need to worry about. So there is a negative sign. What must be the value y that you must multiply this by in order to cancel this? Okay, so can someone tell me? Should I ask the question again? Here are m rows, and this part of
Zi minus, so yi should be Zi minus ci xi by b minus axi.
Yeah, but right now we don't have any variables. We have only a matrix of scalars here and a row of scalars. I'm asking, what should I multiply this matrix of scalars so that when I add to this part gets cancelled? And this is a non-singular matrix.
Yeah, so AB inverse into CB transpose.
Sorry, AB?
AB inverse minus AB inverse into CB transpose.
No, when I add, it should cancel. So don't say minus. And I'm asking for the value of y transpose, just y transpose.
Okay, so AB inverse into CB transpose.
No, so I think you are saying the right thing, but what do we know? Y transpose times AB bar, A bar, yeah, A bar, because it's the extended matrix, must be equal to CB transpose. So what must be Y bar, Y transpose?
Sorry, CB transpose AB inverse.
Yeah, yeah. So it's the other side. Yeah.
Okay.
So I don't know what's going on. So let me erase this. And is it clear to everybody? Yeah. There is a non-singular matrix. I shouldn't have erased this. That multiplied by Y bar should give you this value. So we don't have a choice. Yeah. So we can guess if strong duality is to be proved this way, there is only one Y bar that we need to work with. Okay. And that Y bar must be, what did he say? CB transpose A bar B inverse. Okay. So we just guess that, let us take this value for Y bar. So we have gone and straight away got our hands on the dual solution, or at least a potential dual solution. And now what do we need to verify? We need to verify that this Y bar T that we have obtained gives us the dual optimum. Okay. Now, all right, so what does it mean to verify that Y bar T is dual optimum? First of all, we need to verify that the objective function of the dual, this matches with the optimum that Simplex produced in the last line. Okay, so that is one thing that we need to verify. And the second thing we need to verify is that this Y bar, which we just did by some inversion of some matrix, is actually a feasible solution for the dual. Once we have done these two, we would have established that this fellow, this Y bar is a feasible solution and its value matches the optimum of the prime. Okay, and we already know that it can't do any better. So let us it's just routine things we need to do. Okay, so let us see. Let us look at this Y bar T. Let's look at Z, which was the last line. So now I'm invoking Simplex. Now Simplex, Z is always C transpose X. Yeah, and C transpose X, I can split this C into two parts, which are the basic part and the non-basic part. And the current basic solution, if your current basis is D, is given by this expression. This is something we wrote about two classes ago. If you're given a particular basis, how do you extract XB from it? And how do you write the objective function in terms of the current XB and current XL? Okay, so this, once you've fixed the basis, this is just standard formula. You just move things from left to right and do this. Okay. Now, let us look at the Primals optimum. Simplex tells us that the Primals optimum at this basis, yeah, is obtained by setting these xn's to 0 and substituting this value for xp. So we have set these xn's to 0 and substituted this value for xb here. So this is the Primals optimum. But notice that I can write this as, yeah, so it is the dot product of this, it is the product of this and this. I'm just taking its transpose. So I'm writing this transpose times this transpose, and this transpose, the CB goes here and this. Okay, now we already had that Y transpose is CB transpose AB inverse. So Y must be AB transpose inverse times CB. So you just substitute. And we notice that this is Y. It is B transpose and this quantity is Y. Yeah, you compare this. This is Y transpose. So this quantity must be Y. So this is just an algebraic way of deriving things. Okay. So we guessed a particular value of y, we substituted it, and from the fact that at this point, this quantity was the primal object optimum. And why do we know that it was the primal optimum? Because we know that simplex, when it terminates, produces the primal optimum. So this is because of simplex. This is just rearranging this. And this is because we have declared this to be y. Nothing happened. Okay. So if we choose this value of y, certainly the objective function of the dual will match the objective function of the primal. But the question is, as I said before, is this y feasible? Now, to check that it is feasible, if you remember, we had inequalities, of the form A transpose y is greater than or equal to 0. Things have become a little complicated now because there is an A bar. We have extended A, so we will have to unextend A. We throw away the columns which were added because of the slack variable and say that for the remaining thing, y is a feasible solution. Further, we need to ensure that y is non-negative. This was not there in our previous argument because with equalities, we did not have to verify non-negativity. Now we need to verify it. So let us do it. Okay. So we know, again, this is just, we are not going to look at the evolution of the simplex process. We are just looking at the last tableau. The last tableau, I'm sorry, I'm getting a phone call. The last line tells us that this is okay. So now at this point, what do we know? If we compare, sorry, what did I do? Sorry, there was, I seem to have made, was there a B here or something that I'm missing on the left? Sorry. So why is, so we know that C transpose X, minus, so I believe, so correct me if I'm wrong. 1 second. Obviously made a mistake. I mean, the left-hand side has no scalars, so there is a mistake somewhere.
I think it is A bar X is equals to B. That's
So, I mean, I should write something like this, right?
yeah.
Sorry, what did you just say?
C transpose X minus Y transpose B, and that after that it will be like C transpose X minus Y transpose A bar X.
So please say it again. C transpose X minus
C transpose X minus Y transpose B. That's like feasibility if we are checking whether they are equal or not. And
but
and then A bar, then that B is like transformed to A bar X because that's the condition.
Sorry.
Okay, I think.
See, we know that the final, when we choose this value of y, this quantity becomes equal to this quantity, if I understood right. So I should actually have written something like this here instead of A bar X, and this should have been a plus, I think. Okay, but let us just check. I don't know what, that's why I think everything is going wrong. So that's why all my inequalities are also. Okay, so let us just check. So what happens is that yeah, no, sorry, we added this. Okay. Just one moment. So you're saying we should just maybe I think we just added here. So there was something wrong earlier also, but doesn't matter. So most probably this is Y transpose B here. Okay, I will correct it in the notes. I need to look at it carefully. But the important thing is this. Okay, so let us continue. Let's leave. I mean, it's a question of routine manipulation, but let us just do it quickly. Okay, so what we know is that the basic variables have vanished from the right hand side, which means that when the basic variables coefficients are extracted out of this, they are exactly cancelling the coefficients of the basic variables here. So that means for each basic variable xj, its coefficient here and the coefficient obtained from multiplying Y transpose with A bar must be the same. Okay, so we get equality for basic variables, and for non-basic variables, the coefficient of x on this side and the coefficient obtained by moving this A bar to the right, they must match. Yeah. But this R is greater than or equal to 0. So we get that this A trans, the row of A bar with Y is greater than or equal to CK. Is this clear? I mean, I'm just saying that since this RK is greater than or equal to 0, I can replace this equality by this inequality. Yeah, so this is true for non-basic, non-slack variables, because because they have a CK. Others, for the others, CK is 0. And if you look at for slack variables, they don't participate in the objective function. So this quantity is 0. And how do they participate in this matrix A bar? They participate by the identity matrix. So each of these variables yk must be at least 0. Okay. Sorry. Let me, I will correct it in the notes, and but the point is this: you look at the final tableau. Now you have this A bar, which is an extended matrix. That A bar has an identity matrix on one side and the rest which we got from before. That was A. Okay. Now, when simplex stops, some of these slack variables might have become basic, and some of those there might be other basic variables. We don't know how the basics arises. But the important thing is for the slack variables, if you look at this quantity, because there is an identity, this quantity for the kth slack variable will just be k. That means the new variable that you added, the kth variable. There were already n variables, and then you added n plus 1, n plus 2, n plus m as your slack variables. If you look at what happens to their coefficient and compare it with the last row of the simplex, you will get this. And for other variables, you will get, okay. So the upshot of all this, had I done this properly, would be that when you look at the final state of the simplex method, you will see that the Y bar that we cooked up, yeah, the Y bar that we cooked up, the Y that we cooked up is actually feasible for the dual program. And so we have proved strong duality for this kind of linear programs. Okay. So any questions at this point?
Why do you have to separately look at this slack variable case? Didn't the previous case?
Why am I looking at this?
I mean, separately, didn't the previous case that we just did subsume this?
No, so I just want to prove strong duality for this kind of linear programs. Last time we proved strong duality for linear programs where there was equality.
Oh, okay.
Okay. Now, so I'm going to sort of reduce the problem to that problem by introducing slack variables. But then this dual doesn't talk about slack variables. So I have to eliminate slack variables in my logic. And my claim is that it can be done. And when we eliminate slack variables, see what is the difference between this dual and the previous dual? This is there. Okay, previous dual didn't have it. Okay, so we are additionally responsible to prove this. In addition, and also we just have to write.
Sorry, could you just show the previous primal dual formulation?
Sorry,
the previous.
Yeah, so the previous primal dual, I don't have it on this slide, but let me write it down. Yeah, so that would have been looked like AX equals B, X greater than or equal to 0. And here it would have looked like A transpose X is greater than or equal to, sorry, A transpose
Y
is greater than or equal to 0, Y unrestricted.
Greater than equal to C.
So, right. Sorry.
Yes, okay, thank you.
Yeah, so it would have, I believe it would have looked something like this. Yeah.
Yes. Okay, thank you.
Now, because we are working with a different linear program, we have this additional responsibility. But my claim is that this additional thing that we need to ensure comes out of the slack variables that we introduced on this side. And if you analyze their role, yeah, for slack variables, basic or non-basic, you will get this. For basic, this will hold with equality. For slack variables, which happen to be in the basis, this will hold with equality. Yeah. And for other variables, it will hold by inequality out of this. Okay. Yeah. All right.
Jaykumar, we needed non-negativity for all variables, right?
Sorry?
We need to show non-negativity for all variables.
Yes, so this is for all variables.
Oh.
Yeah, so that's okay. Let me just say this value K. So originally we had variables x1, x2, xn, and we added new slack variables xn plus 1 to xn plus m, and we stuck in an identity matrix here. And the variable corresponding to this row was y1, y2, ym. So there are only m variables for which we need to ensure non-negativity on the dual side. And the first of those yi's will get its non-negativity out of analyzing the first slack variable, the second from the second slack variable, and the mth from the mth slack variable.
Sure,
that is what I meant to write here. Sorry.
Sure.
Yeah.
Thanks.
Okay, yeah. I'm sorry. Yeah, but let us move on. I think it is the same thing over and over again. But now I want to move to inequalities. So we will again say duality once more for a different kind of linear program. But I want to do this somewhat more geometrically, yeah, meaning there'll be some geometric intuition in what we discuss now. And so I'm moving from our text to a book of Shriver's on linear and integer programming, chapter 7. Okay, you don't need to, everything that we need, I hope I will cover today. Yeah. Okay, so in the next 1 hour, I want to tell you about what Shriver calls the fundamental theorem of linear inequalities. It is very similar to some version of Farkas lemma. So let me just say what the theorem says. That suppose you have been given some vectors a1 to an and an additional vector b. So we have given these n plus 1 vectors, in an m-dimensional space. And let's assume that these vectors together span the whole space. They span the whole space. Okay. Now let us write these vectors a1 to an as column vectors. So then the fundamental theorem of linear inequalities says this: either your vector b can be written as a non-negative combination of the columns of A, which means the vectors AI. Either this is true, or there is a hyperplane, defined by this C, so that the entire cone is on one side and B is on the other side. Okay, so ignore this statement for the moment. Either it is the case that this vector is in the cone. Now, what do I mean by the cone? You take positive linear combinations. So you scale all these vectors by, you can't scale them by negative numbers. Don't allow them to go backwards. Yeah? Scale them by some non-negative numbers and add them up. And geometrically or intuitively, it will produce all vectors in this cone. Yeah. Okay. So either your B is in this cone, or it must be that B is somewhere outside, in which case there is a hyperplane. Yeah. So this point is the origin, is 0. Yeah. So there is a hyperplane, so that this vector B is strictly, this is a strict inequality, strictly on this side, and the entire cone is on the other side. Yeah. Furthermore, this particular hyperplane, it rests on the cone. That is, there are m-1 linearly independent AIs, and this hyperplane passes through them. Yeah. So maybe I should draw a picture somewhere. Yeah. So suppose we are in 2 dimensions. So maybe I should just create a page. Where am I? So suppose we were in 2 dimensions. Yeah, and there was some cone. Yeah. So if you take your vector B, either your vector B is in this cone, or there is a hyperplane. Which hyperplane? This line itself. Yeah. This line which separates this. So in this case, what is M? M is 2. We are in 2 dimensions. And there is a hyperplane which includes one of the AIs, A1 and A2. A1 and A2 were these 2 vectors which generated this cone. And if it is the case that your B is outside, then if you look at this normal, then the entire cone is on one side of this half of this hyperplane, and B is on the other side. Okay. So now suppose, I hope, look at me. Okay. So suppose you had a cone with flat faces, yeah, in 3 dimensions, and there is a point outside. Yeah. Then there will be some plane, intuitively at least, which separates this cone from this point B. But furthermore, actually, I'm claiming that we can place that plane flat on this cone. So one of the flat parts of this cone, one of the flat sides of this cone, will serve as the separator between this point and this. Okay. So
sorry, could you please show the statement of the theorem? Yes, thank you.
So either it is the case, Yeah, so maybe the second part. Yeah, so I had told you to ignore this. Now so of the vectors that were there, A1 to AN, there will be A1 to AN. There's a huge number of vectors initially. You can get some M minus one of them so that this hyperplane actually passes through them. Yeah. And these are linearly independent. So in effect, this hyperplane is an M minus one dimensional space because we are in an M dimensional space. And this hyperplane is actually being spanned by some M minus one of those vectors. Okay. So there's some.
Sorry, I'm a bit confused. So n is the rank of these vectors, right?
Sorry, what is the
M
rank?
is the M is the
Yeah, M is the rank.
So there are n vectors, and you are saying just from the first n vectors I can find.
I can't. There are n vectors. N.
Yes. Okay. So and you are claiming just from the first n vectors I can find a separating hyperplane. Is that right?
Sorry. Linearly independent. This n is wrong. Is that your problem? This I just meant. Sorry.
Okay. Yeah.
I'm sorry. Yeah, I just meant some m minus one linearly independent vectors from.
Yes. Sorry. Yeah. Also the last one actually does not give a certificate separating hyperplane, right?
Sorry, I made a mistake again. I agree. The thing is, my n and Shriver's n are different. I wanted to be consistent, and I made a mistake. Yeah. Is this okay now? Thank you very much.
Yes.
Yeah. So this hyperplane, everything is on one side, B is on the other side, and and furthermore, this hyperplane, the orange hyperplane here, rests on m minus one vectors out of A1 to AN. Yeah, no first, last, etc. Some m minus one linearly independent vectors. Okay, good. So I want to prove this. Yeah. Now, if you can find such a hyperplane, then it is easy. This is like weak duality. Then it will not be possible for you to write B as this. So only one of them can hold. So yeah, if this holds, then this cannot hold. You can check that. Or sorry, what am I saying? So I don't know what I've written, but
yeah, one implies not two is trivial, right?
yeah, one implies not two is what I should have written. It's feasible. Should I write it infeasible? I don't know what I'm doing. Just 1 second. Let me look at the book. Just copy everything down. So I shouldn't write such things. So suppose one is true, then two cannot be true. Is this what you said? Yeah.
Yes.
If there is a vector here, there is no way you can separate it from this. Because, yeah. So this is like weak duality. Now what we want to say is that if one is not true, yeah, that is, if B cannot be written as a non-negative linear combination of the AIs, then there must be such a normal vectors. So yeah. So if 1 is not true, then we want to claim that 2 is true. Yeah. So there are many ways to establish the existence of this C. You can write this problem itself as a linear program, and from strong duality you can extract C. You need to work a little harder to ensure that that C that you get corresponds to a hyperplane that rests on m-1 linearly independent vectors. And for some later purposes, that particular clause that the hyperplane rests on m-1 linearly independent vectors will be important for us. So it's not just some extra thing that has been added. It will be useful for us later. Okay. So what I'm going to do today, I'm slightly running out of time, but please stop me nevertheless, especially if I make such mistakes. Okay. So we are going to use some sort of a simplex method to show that there is such a hyperplane. Okay. And so what was it? Okay. So let's start. Yeah. So the first thing is, we may assume that the cone that A1 to AM produces, that is already full dimensional. Okay. Because if it was not full dimensional, then we know that A1 to AM together with B span the whole space. That means the entire subspace spanned by A1 to AN, A1 to AN, does not contain B. Okay. So then we can just take that subspace, which is m-1 dimensional, which is spanned by A1 to AN, and look at its normal. Then B will be not even on that subspace. Forget the cone. Yeah, B will not even be in the subspace, and we would have found the hyperplane. Okay. So the interesting case is when A1 to AN, they span the whole space. Okay. Also, we can assume that this B, the vector which we are trying to generate out of A1 to AN, is not equal to 0. Otherwise, obviously, it is in the cone of A1 to AN. So we are assuming that if the first condition doesn't hold, if B is not in the cone, then we can find such a hyperplane. But if B is 0, then it is definitely in the cone. Okay. So we can assume that B is not 0. Okay. So now what do? I'm going to do some sort of a simplex method. It will remind you of simplex method, but it will somehow be simpler than simplex method. Okay. So let me just explain. I'm going to show you an algorithm to construct that hyperplane. Okay. Yeah. So what do? So how do we start? Okay. So you have this vector B, which is not 0, and B together with the AIs span the whole space. Okay. So I'm not going to worry too much about the indices. Let us say that we extended B to a basis for the whole space. Okay. So we took B and we added some m-1 of the A's. Okay. I mean, don't take these indices very seriously. We have taken B together with some m of them, and this has formed the basis for the whole space. They are all linearly independent. Now take this part and consider the hyperplane generated by them. Okay. So this is the hyperplane that passes through A1 to AM-1 at any time. Okay. So this is this funny kind of simplex. At any time, what we are going to ensure is that the current hyperplane passes through some m-1 linearly independent vectors. So initially, we will just guess a hyperplane, and we just do it very naively. Okay. Take A1 to AM-1, which are linearly independent of B, and just take the hyperplane passing through them. Okay. And we found this hyperplane. No? This was meant to be a hyperplane. Okay. So this hyperplane, and you see A1 to AM-1 are sitting on the hyperplane. And this hyperplane has a normal, and we orient the normal away from B. Okay. Now, the question is, are we done? Are the conditions for the second number 2, are they already met? Well, B is on one side. The hyperplane is like this. It passes through m-1 linearly independent points. But the thing that could go wrong is that there might be some elements of A, of some of the AIs, which are on the same side as B. Yeah. In that case, we need to pivot this hyperplane to obtain a new hyperplane. Okay. So we will probably construct another hyperplane and make sure that this A is away from B. But in the process, maybe some other vector goes on the same side as B. Okay. Again, we'll do something. Again, we'll do something, and we will show that this process terminates. Okay. So now, how do we move from this hyperplane to a new hyperplane? Good. So we have got this hyperplane. Let's call it H1. And this hyperplane does not do the job because there is some AI which is on the same side as B. Now, there might be many AIs which are on the same side as B. So among them, we are going to fix one. And which one? The first one, the one with the smallest index. Okay. So this is like Bland's rule, which is we are always going to, whenever we have some AIs who are complaining that they have been put on the same side as B, among them, we take the one which has the smallest index. Okay. So now we have got these m-1 vectors and this vector AI, yeah, these points, and clearly this AI is not in this subspace. So together they form a basis. Together they are linearly independent. Okay. So now we would like to include AI in some hyperplane and drop one of these edges, one of those edges which were in the old hyperplane. Okay. So we are going to twist so that the hyperplane includes AI but excludes one of the other hyperplanes. So now, whom to exclude? Yeah. And how do we ensure that when we add AI and we exclude somebody, B doesn't fall on the same side? Or, so here is what we do. Look at all these A1 to AM. Yeah, look at all this. So right now, not A1 to AM, A1, A2, AM-1, these were already in the whole hyperplane. Is that clear? And now we have added this AI also to it. So they form a space, they form a basis for the current space. Now, can this be in the positive orthant of this A1 to AM?
That is a positive linear combination of the basis vectors.
Yeah. If it was in the positive orthant, then it would be a positive linear combination of A1 to AM. Yeah. But we assume that B is not in the positive orthant. So when we write B as a linear combination of those vectors which were already on the hyperplane and this vector, one of these coefficients must be negative. Okay. They cannot all be non-negative because then B would be in the cone generated by these vectors. Okay. So some alpha I must be negative, some alpha j, yeah, one of the alphas in this row must be negative. Now, we just recently added this vector. Could it be that this alpha j itself, this alpha I itself is negative? Well, that is not going to happen because if you look at, if you take the dot product of both sides with C, yeah, this with C1, this side gives negative, all these quantities give 0. The dot product with AI was negative because it was on the same side as B. That means this alpha I better be positive. So we know that one of the coefficients of these AIs, including one of these coefficients of these A's is negative, but we have ensured that it is not this one. This one is definitely positive. So there must be one of these other coefficients which is negative. And what we are going to do is we are going to drop one of the AIs whose coefficient is negative, okay? Whose coefficient is negative, and take the hyperplane spanned by the remaining m minus 1. Yeah. Now, there might be a choice. There might be many alpha i's here which have negative, which are negative. Which among them should we drop? Again, Bland's rule. Take the first one. Look from the, yes, arrange these AIs. So initially the A's have been arranged in some order, A1, A2, A3, A4, so on. Okay. And among these A's, yeah, drop that one where the index J is the smallest. Okay. So you had this initial hyperplane. This was your AI. These were the vectors that you retained from the original hyperplane. This vector you sacrificed. You sacrificed because its alpha was negative, and you built this hyperplane. It has these m minus 2 plus this one, m minus 1 AIs again. So we always maintain the invariant that m minus 1 of these vectors are there. Okay. Now, and we look at its normal. Yeah, maybe it should be called C2. Yeah. And we arrange it so that B is on one side. And so okay. So yeah, so the other thing to verify is 1 second. So these points which are currently on the hyperplane, yeah, on the current hyperplane, I call them anchor points. Okay, anchor points. So at any step, we have some points which are anchor points, and those anchor points keep changing. Okay. So we have moved to a different set of anchor points, and they are defining a current hyperplane. Okay. We can ask, does this hyperplane do a good job? Well, with respect to this hyperplane, it might be that there is some other point here which was earlier being served well by the earlier hyperplane, but the new hyperplane is creating a problem. So we just repeat the whole process again. Okay, so at any step, you have a hyperplane, B is on one side, yeah, B is not on the hyperplane, yeah, and we ask whether that hyperplane does the job. Otherwise, we shift. And again, go through this two-step process. Among the vectors which are on the same side as B, pick the first one, add it, and remove someone whose coefficient is negative. And we will always find it. Otherwise, B would have been in the positive orthant described by the anchor points and the new entrant AI. Okay. So I have not written this in general. I have described the first two steps, but the same steps you keep doing. Okay. Is this clear?
Yes.
So we keep doing this. Now the question is, why will we stop? Yeah. Is it possible that we cycle? Okay. And basically what we are going to do now is to show that we will not cycle. And why will we not cycle? Okay. And this is basically the proof that Bland's rule works. But we are doing it, Bland's rule, for this system of inequalities. Okay. So suppose these are all the n vectors, A1 to AN, which were describing our cone. Yeah. And as we went, initially there was some set of anchor points, anchor points, anchor points, anchor point changed, anchor point, and suddenly we jumped back to the same And now we have entered a cycle. And we want to derive a contradiction. We want to say that this cycling cannot happen. Why not? Okay. See, at any
anchor point is the variable you leave at a step.
Sorry, say that again.
So anchor point is the point you leave while going from hk to hk plus 1. Or
No, say that again. I can't.
Can you repeat the definition of the anchor point?
Sorry. Say it once more.
Could you repeat the definition of an anchor point?
Anchor point is those points which are those linearly independent points which are on the hyperplane.
Okay.
Okay. Basically, they determine the hyperplane. So initially, we had this set which was the set of initial anchor points. Then one of these was dropped, and AI moved in. So AI together with those m-2 from here, they form the current anchor points. And then somebody else will enter and somebody else will leave. And those will be the current set of anchor points, and so on. Okay. Now, if these anchor points were changing at every step of the simplex of this algorithm, some change happens. Some vector comes, some vector leaves. Okay. Now, if there is a cycling, there must be some AIs which sometimes enter and then leave and enter again and leave, enter again and leave in the life cycle of this cycle. Okay. Among all these variables, so some variables are such that they always sit in the basis. They never leave the basis. There are others who are outside and never come into the basis. They are not involved in the game at all. But there are vectors which are involved in the game in the sense that they come and they leave. They come and they leave. Those vectors, I'm calling them fickle. Yeah, they come and they go. They are not stable. Okay. Among them, focus on the last. So this is the last fickle variable. Okay. That means there was a moment when AR entered the basis, and then there was a later moment when it left the basis. Again, at some point it entered the basis, left the basis, and so on. Whereas these, which are after AR, they are stable. They are stable in what sense? They are stable in the sense that if this one is in the basis, it never leaves the basis. Or somebody is not in the basis, it never enters the basis. So these are completely stable. Okay. And among the fickle variables, this is the last. Some of these could also be stable, but we are not concerned with them. Among the fickle variables, this is the last. The fickle vectors, this is the last. Yeah. It enters the anchor and it, sorry, I kept saying basis. I meant it enters the anchor and it leaves the anchor. Okay. Yeah. So is this okay? Can you all hear me still? Something happened on my screen.
Yes, we can hear you.
Yeah. Okay. Yeah. Okay. So we are about to derive a contradiction from the fact that there is focus on this last fickle variable. Let us see. When this variable entered, why would it have entered? At some point, it entered the anchor set, yeah, AS plus 1. That means at step S, we had a hyperplane HS. There were some points on the hyperplane, and this AR, this is the last fickle. The last fickle variable was on the same side as B. Yeah, this last fickle variable was on the same side as B, and among those which are on the same side as B, it was the one with the smallest coefficient. So what do we know? That at that point, all these fellows, they were being served well by the current hyperplane, HS. They were on the other side as B. The first vector, which was on the same side as B, was AR. So at this moment, B is on one side of, this is the normal to this hyperplane. B is on one side. AR is on the same side, but every AJ for j equals 1 to r minus 1, every AJ is on the others, not on the side of B. It's on this side. There might be some others, but they might be after R. But before R, everybody before R is either on the hyperplane or on this side. Is this clear? When AR entered the basis, these conditions used to hold. Is this clear?
Yes.
Okay. Then there was a moment when AR, sorry, why do I say A? Yeah, AR left the basis. Yeah. I don't know what I'm doing, but so sorry, I made a mistake again. This should have been. So there was a moment when there was a basis, and at that moment, AR was forced to leave the basis. Now let us ask, why would it have left the basis? When does somebody leave the basis? You write B at that moment as a linear combination of this. Again, don't pay too much attention to these indices. I've actually written all the AIs. Okay, so we would have written B as a combination of these, but only the current anchor points. Yeah. So this AJ is about to enter the basis, and it is going to throw out AR. This AJ is going to enter the basis and is going to throw out AR. Okay. And there were, this AJ is going to enter the anchor set and throw out AR from the anchor set. Okay. Yeah. Keep saying basis. Yeah, I meant anchor set. Okay. Now, why? We wrote B as a combination of the current basis. That is the previous anchor set together with AJ. Yeah, AJ wants to enter. And in this was the first negative coefficient. All these coefficients were non-negative. Yeah. So there are two facts. When AR entered the basis, this CS, yeah, all the other previous AJs were on the same side as this hyperplane. When AR enters the basis, the previous fellows, their coefficients are either zero, that is, they didn't even participate in the basis, or if they did participate in the basis, the previous fellows' coefficients were all non-negative. Okay. Now, let us take this equation and take its dot product with this normal vector. Which normal vector? This equation was generated at a time t, yeah, when AR was about to leave the basis. I'm not looking at the normal vector of that time. I'm looking at the normal vector when AR entered the basis. Yeah, and take its dot product. At that time, since B was on this side, the dot product with this should be negative. Yeah, CS was pointing in the wrong direction. Whereas AR was the first fellow. Yeah, AR at that point. Yeah, so what can we say about, let us look at, so take the dot product of CS with the right hand side here, and let us quietly analyze what happened. Now, in this quantity was definitely non-negative because AR was the first one who wanted to enter. The others didn't want to enter. That means the hyperplane CS was treating them well. That means it was giving them a non-negative value. What about these alphas? AR is the first alpha, which is negative. So for them, this is also non-negative. This is also non-negative or positive. So all these quantities, I say positive, but I meant non-negative. Okay, so all these are non-negative. These quantities, okay, these CS, every vector here either is not participating in the current base anchor or current basis, or it is already on the hyperplane and it used to be in the old hyperplane as well as the new hyperplane. So that means the dot product with CS for them was zero, or the coefficient alpha itself was zero. So all these guys are contributing 0. All these guys are contributing non-negative. Okay. Let us analyze this term. This alpha was negative. That's why it left the basis. And this, was negative. That's why it entered the basis at time S. At time T, it left the basis because the coefficient was negative. At time S, it entered the basis because this quantity was negative. Two negative numbers, product of two negative numbers is positive. Okay. So what do we get? 0 is greater than a positive constant, which is a contradiction. So cycling cannot happen. Is this clear? Once again, there was a certain process of pivoting the hyperplane. Okay, we are always going to
the stable points that lie outside the hyperplane. Why is the product with them 0?
The stable points that lie outside the hyperplane
always lie outside the hyperplane.
Yes.
Why is their dot product with the normal 0?
Because they did, since they are always on the hyperplane, their alpha itself is 0. Then the dot product need not be 0, their alphas are 0. Because although I have written this like this, the only coefficients that I write here are the coefficients that come from the current basis.
Okay, right.
Okay. I mean, I didn't want to play around with indices with double subscripts. Okay. So I've written all of them, but you should understand that the only alphas that participate here are m of them. The other alphas are 0. Which m? There was the current anchor point and one more point. That's all. So these things on the right, they were always in the hyperplane, or they were always outside the hyperplane, which means they didn't even participate in this basis.
Okay, thank you.
Yeah. So just, sorry, are there more questions? It's not so bad. Yeah. So what do we prove? That if B is outside, then we will be able to always shift our hyperplane. Somehow it dances around and settles at a point so that the entire cone is on one side. Furthermore, it is resting on one of the sides of the cone. Questions? So I've already, okay, so now I want to derive, sorry, everybody is leaving or something is happening. Is everybody there? Can you hear me?
Yes, very much, sir.
Yes.
Good. So I want to now apply this theorem, this fundamental theorem of linear inequalities, to prove a very, very nice result about cones. Okay.
So, sorry. So, for example, if we apply this to Farkas lemma, would this say that if Ax equals to B, x greater than equals to 0 does not have a solution?
Yes.
Then the other equation will have a solution where y is a linear combination of the rows or something like that.
Yeah, I'll have to think, but yeah, something like that. That is y, will come out of, I'll have to, I mean, there are many versions of Farkas lemma, but we can go over it. But right now, let us, it tells you that the hyperplane that separates it is not just any old hyperplane. It achieves equality on some m-1 coordinates, for m-1 vectors. Okay. Yeah, so I'm not able to immediately kind of see which version, but once we write it down, we will know what this implies. Yeah. It is like Farkas lemma with a slight strengthening. Okay. And very soon you will see why I'm so obsessed with this strengthening. Okay. So anyway, I have been using the word cone, but what does cone mean? Cone is a set with this property that whenever two vectors are in the cone, then their non-negative linear combination is also in the cone. So so take two vectors, take their non-negative linear combination, that will be also in the cone. So, but you should, in your mind, imagine it to be an object like this. Okay, yeah, like this. The half space is also a cone, because whenever you take two vectors, then you take any linear combination, non-negative linear combination of them, that is also in the half space. Yeah, so this closed half space. Yeah. Rays, yeah, they are cones. If you take this kind of a slightly annoying cone, but if you take a line like this, yeah, that is also a cone. Now we'll be talking about polyhedral cones. So look at all those points which satisfy ax less than or equal to b. So ax less than or equal to b is a set of closed half spaces, and you are taking the intersection of some finitely many closed half spaces. Okay, and such an object is called a polyhedral cone. Is this clear? A cone which has been generated by some half spaces, that is called a polyhedral cone. Okay. And finitely generated cone is you take some points, which is the kind of thing we have been doing. Yeah, you take some points a1 to an and take all non-negative linear combinations of them. All the points that you get, we call them that is a cone, because if you take any two such points and take a non-negative linear combination, it will still be a non-negative linear combination of some points. So this is called a finitely generated cone. Now it's very closely related to ideas that we have talked about long ago. That is, what's a convex polyhedron? It is, the only difference is that the right hand side, instead of 0, we write a b. Okay, and a convex hull is the analog of a finitely generated cone, and they are more closely related. We will see very soon. Okay, yeah, but it is an object like this. That is, you take the average of the points x1 to xn with all kinds of weightings allowed. Yeah, all. Yeah. So that is convex hull. Okay, so these are things that you are familiar with. Yeah, maybe you have not seen this before, but is it clear what polyhedral cone and finitely generated cone are? Yeah, one is defined in terms of equations, the other is defined in terms of points. Okay, and we are basically leading to that big theorem in convex geometry that when you have a polytope, yeah, polytope can be described as a bounded polyhedron. Yeah, that is a set of hyperplanes, half spaces, intersection of half spaces, which happens to be bounded. Okay. But one also likes to imagine a polytope as consisting of vertices, and you have taken the convex combination, that is the convex hull of the vertices. So is it true that anything that can be generated by half spaces can also be generated? There is a set of vertices, a finite set of vertices, which will generate exactly the same polytope. Okay. Now, this is true, of course, and we intuitively believe. I mean, it's hard to imagine why it could be false, but it needs some proof, and we are proceeding towards that. And the fundamental theorem of linear inequalities will come into play there. Okay. So, what is the theorem? So, leave the polytopes aside. Yeah, and so convex cone is finitely generated. Yeah, so we have a cone. Yeah, so we are only talking whatever we have defined as cone is convex cone. Huh? Yeah, so ignore this word. So if your cone is finitely generated, if and only if it is polyhedral. Okay, that is, if you give me a set of points and describe the cone generated by them, then I can give you a set of equations, inequalities, which will generate the same cone. If you give me a set of inequalities, I'll be able to give you a set of points which will generate the same cone. generate in the sense of non-negative linear combinations. Okay. Now let us see. So suppose, so we are trying to prove this. Yeah. So suppose you had some point, some set of points. What did I do? And look at the cone generated by them. Yeah. My claim is that this cone is generated by a finite set of inequalities. Okay. Now, those inequalities, what is the responsibility of an inequality? The responsibility of an inequality is to exclude everything which is not in the cone. Yeah. So anything which is not meant to be in the cone, yeah, here, anything which is not meant to be in the cone should be separated out by one of the inequalities. What does the fundamental theorem of inequalities tell us? What does it tell us? It tells us that for every point which is not in the cone, there is a hyperplane which separates them. Okay, so we could take the set of all such hyperplanes and say that I'm going to take the intersection of them. But if we just lived only with hyperplanes, there might be infinitely many hyperplanes. For each point, a different hyperplane is separating it. But what does the fundamental theorem of inequalities, that extra clause, tell us? It is not just any old hyperplane. A hyperplane which can be determined by picking m-1 of the endpoints. Yeah. So we don't need to run through all possible imaginable hyperplanes which separate this cone from other points. Go over all the m-1 size set, m-1 size subsets of the points a1 to an, which were generating the cone. See if they produce a hyperplane, on which the cone rests and is on one side. Include that hyperplane in your definition here. Yeah. And do this for all those hyperplanes. There will only be a finite number of them. Is this clear? So this is where we used that stronger property that we proved. Is this clear?
Yes.
So if you have a finitely generated cone, we can describe it by equations. One equation for each of those, perhaps at most n choose m-1 subsets. Yeah. Now we want to prove the other direction. Okay. And we are going to assume that our cone is polyhedral, and we are going to say that it can be finitely generated. So how? So let us look at this polyhedral cone. Yeah, so I hope you can see this. Is this clear enough? Okay. So this polyhedral cone is defined by some equations. Yeah. So this equation says that you should be on this side. Yeah. Yeah. So these equations are a1x should be less than or equal to 0. That is, all points of the cone should be pointing away from this normal a1. This says all points should be pointing away from a2. Yeah. So these ai's, you should think of it as outward normal to those hyperplanes. Yeah. So now this is the trick. Yeah. It's almost, look at these ai's. They are also vectors. And consider this cone n generated by those normals. So that is this cone. What did I do? I took the normals for each of those hyperplanes which participated in this definition. Temporarily, I forgot about this cone, wrote down those things, and produced this cone. Now, this was a polyhedral cone, and this one is a
generated
finitely generated cone. Yeah, it's a finitely generated cone. Yeah. And now, what do we know about finitely generated cone? We have proved this direction. So this finitely generated cone also can be written as a polyhedral cone. Okay, it might temporarily appear that I'm doing everything in a circular fashion. It is not circular. Okay, hopefully, yeah. So we were given this polyhedral cone. We looked at the normals. We generated the cone out of the normals. That was this cone. This cone had its own, so to say, faces. Yeah, it was generated by these equations, these inequalities. Okay. Now, look at the cone generated by this. What sort of cone is this?
finitely generated.
It's a finitely generated cone. And my claim is that this cone will actually be the same as the original cone. That is, you take this finitely generated cone, turn it into a polyhedral cone using the first part of the theorem which we are proving. Look at the normals here. And the claim is that this original cone was the same as this cone. That is, if you look at everything generated by these BIs, that will be the original cone. Let us prove it. Okay, and then we will stop for the day. There are things to do which I wanted to do after this. That is, come back. This theorem implies the theorem about polytopes. I will do that next time. So far, is everybody with me? Okay. We are using the fundamental theorem of linear inequalities to prove that every polyhedral cone is a finitely generated cone and every finitely generated cone is a polyhedral cone. We have already proved that every finitely generated cone is a polyhedral cone. Okay. Now, what do we need to show? We need to show that this cone is the same as this cone. So there are two things to show. Is this cone contained in this cone? And could it be that there are points in this cone which were not covered by this cone? So first we will show that everything in this cone is contained in C. Let us see. Look at this BI. We need to show that each of these BIs is in the original cone C. If we show that each of these BIs is in the original cone C, then their entire non-negative linear combination will also be inside C because C is closed under non-negative linear combinations. So we need to show that each of these BIs is in this cone. Okay. Now, what are these X's here? See, these were X's which were generated. N was the cone generated by these AIs. So in particular, this N contains each of these AIs. Is that clear? Each of these AIs is in N. Yeah. That means each of those AIs satisfies all these equations. That means AI, each of those AIs and B1. Focus on B1. B1 with each of those AIs, yeah, gives a negative dot product, a non-positive dot product which is less than or equal to 0. That is BI, yeah. So each of those AIs and B1 with each of those AIs gives a negative dot product, which means BI with each of those AIs gives a negative dot product. That means BI has a right to be in this cone because its dot product with each of these AIs is less than or equal to 0. Yeah, each of those AIs is part of this cone because it was generated by them. Yeah. So we know that each of these BIs has non-positive dot product with each element of n, and in particular, n includes all the AIs. So each BI has a non-negative dot product with each of the AIs. So BI must be in this cone. Okay, so we have proved this. Is this clear? Sorry if most people are quiet and I don't know.
Yes, it's clear.
Yes.
It's clear? It's clear. Yeah.
Yes.
Yeah, it's clear. Okay. So what could go wrong? Yeah. What could go wrong is that here was your original, sorry, just give me 2 minutes. Yeah. Here was your original cone, which was generated by, which was some polyhedral cone. But yeah, this was this cone. And now you put your BIs. We know that these BIs, they generate a cone, but we are worried that cone is definitely inside this. Yeah, so this cone is inside this outer cone. Yeah, but could it be that the outer cone includes points? The original cone C has some points which are not in this. Yeah, that is what we are worried about. And we want to say, so suppose there is a point X, yeah, X, which is, 1 second. I'm sorry. So there is a point X, which is not in this cone generated by the BIs. Yeah. So suppose there is a point X, which is not in this, and we want to claim that that point is also not in C. Anything that is not in B, in the cone generated by the BIs, is also not in C. Okay, why? If there is a point which is not in B, then in applied appeal to the fundamental theorem, there must be a hyperplane which separates them. Let us call that hyperplane W. What property does the W have? It, okay, so this time I'm taking, W is pointing in the other direction. So this W has a positive dot product with this vector X, which is not in this cone. Yeah, it has a positive, and its dot product with the BIs is less than or equal to 0. So W is an element, yeah, which has dot product less than or equal to 0 with each BI. But W's dot product with X is positive. Now, who are the fellows whose dot product with each BI is less than or equal to 0? That was the very definition of N. N was all those elements whose dot product with each BI is less than or equal to 0. That means this particular point X, the pretender, yeah, has a positive dot product with all the elements of N. Yeah. Sorry, no, with an element of N. Yeah, there is an element W in N. Once again, let me start. W happens to be a vector which has non-positive dot product with each BI. So W is one of these. That means W is in this N. But every element of N has the property that, sorry, every element of X has non-positive dot product with every element of N. Every element of the original cone has non-positive dot product with every AI. Hence, every element of X has non-positive dot product with every element of N, because every element of N is just a cone, is a non-negative linear combination of this. So this element X, the pretender, unfortunately has a positive dot product with an element W, which is in the cone N, but every element of N is supposed to have negative or non-positive, I'll say negative dot product with every element of X, every element of C. So this X could not be in C. So let me read this out. So this W must be in N. Since N is a set of valid outward normals, every element of N is a valid outward normal for the original cone. Okay. But this X seems to be in the same direction as an outward normal. So X cannot be in C. Okay. It looks like I pulled a fast one. Yeah. I seem to have proved one direction and somehow used it again. Okay. Yeah. But it's really pretty if you can get it. Please ask me a question. I'm gone over time, but we can spend a couple of minutes. Kavita, you wanted to say something.
What is the relationship between the B's and A's?
Yeah, so it is slightly, I mean, it's a two-step, it's 2 degrees of separation. Okay, so C was the original cone. That cone had normals, AIs. These B's were the normals of the equational form, inequality form of this cone N. Once again, this was the original cone. Yeah, these were the normals that described the original cone because it was a polyhedral. Look at those AIs and consider the cone generated by the AIs. It will have some faces, and look at the normals to those faces. Those are the BIs.
Sure, but there is no sort of easy relationship between.
Yeah, it might well. I mean, their numbers, nothing, because all we have is N choose M. So there is no. But in general, one should sort of believe in good situations that perhaps the normals. Yeah. So directly from B's we don't get. Once we take, yeah.
Sure, thanks.
So let me just leave you with a little exercise. Yeah. Just to see whether you understand, whether you even believe this. So let us look at this half space. We agreed that it's a cone. Yeah. Is it a polyhedral cone?
This is not bounded.
Yeah, it's not bounded. But is it can it be defined by something which looks like AX less than or equal to B? Yeah, something like that.
Yeah, so the first coordinate is non-positive.
Yeah, so
non-negative.
Yeah, something like that. X2 is greater than or equal to 0, or minus X2 is less than 0, or something like that. Yeah. So this is a polyhedral cone. Yeah. Now it's also finitely generated. Okay. So which are the vectors which generate this cone? Somebody? I hope the upper half space. Which are the vectors which generate this cone? Sorry, what happened?
The normal.
Sorry, one minute.
So if you look at the normal vector, that only generates this. Yeah. That will just be a ray.
The standard positive, the standard basis vectors except the second E1, E3, E4, En.
No, it's 2 dimensions. We are talking about 2 dimensions. There is X1,
So,
X. Yeah.
Just E1 generates this. Right?
E1 and?
E1 and, okay. And a normal.
So E1 and normal would generate this positive orthant.
So, okay, not E1. E1 plus E2 and E2, they should generate this.
They also generate the positive orthant. E1 plus E2, E1 plus E2, and this.
minus C1 plus.
Thank you.
Oh,
Yeah, it's annoying. Yeah, it's annoying. One would have thought this is somehow a cone generated as two sides. No, actually, it is generated by these three. Yeah. Now we start suspecting, is this theorem even true? Okay. So what I would like you to do is run this example through this. Okay. So here is a finitely generated cone. And if you went through this proof, yeah, would it generate this inequality? Yeah. And go through this proof with this inequality. Would it generate these three rays or maybe these three rays? Yeah. Which three rays will it generate? Okay. Yeah. Good. So I'm running out of time. 1 second. Yeah. So can we stop? Is everybody? Is there a questions we can ask? I'm sorry, I've really gone over time today, and I've not even covered everything. Don't worry. Yeah. Next time. Any questions, please? So I'll put the notes anyway. Yeah. Feel free to read through them. Yeah. So let me just say one last thing, 1 minute. So it turns out that any polyhedron, yeah, any polyhedron, not necessarily a cone, is actually looks like a polytope added to a cone. You see, any polyhedron, yeah, will be an object which has a conical, a polytopal base followed by a cone. Yeah, so it will have a little base and a cone. Yeah. So there is some sort of a polytope sitting here, and then there is a cone sitting here. And if you add that cone to this polytope, you will get this picture. Okay. Yeah. And that is a theorem that I was supposed to prove. And then, yeah, then a geometry of LP duality, all that next time. Yeah, we are a little slow, but it's okay. I didn't prepare properly. Okay, good. Any other questions? Okay, thank you.
Thank you very much.